Hi, everyone. Welcome to this session of the Statistical Physics Journal Club Talks. We are honored today to have Abhishek Dhar as our speaker. Uh, he's a professor in the Stat Physics group at ICTS. And today he'll talk about his recent work on a microscopic derivation of nonlinear fluctuating hydrodynamics. So yeah, over to you, Abhishek.
Yeah, thanks. Sure. So first, I would like to thank Saurabh, Jitendra, and Prashant for organizing this nice series of talks and also asking me to talk about this. So yeah, so today I'm talking about this work on microscopic derivation of fluctuating hydrodynamics, and this is work done with some colleagues at Japan, Keiji Saito, Masaru Hongo, and Shinichi Sasa. And this has appeared in a preprint, and here's the reference. And I would like to thank Orithro and Anupam, with whom I have had lots of discussions on this topic. Okay, so. Okay, so here's the outline of the talk. So I'll just give a lot of introduction about the basic idea of hydrodynamics and how we use it. So one can use hydrodynamics out of equilibrium, and then, but also one can understand a lot of properties of systems in equilibrium using this framework of nonlinear fluctuating hydrodynamics. And then I would like to just explain that there are these two pictures of hydrodynamics, of fluid picture and particle picture, and they are just two ways of describing the same system, and one can transform from one description to the other description. Like if you have a fluid, we'll be looking at strictly one-dimensional systems, and you can have an anharmonic change, which is, or you can have like a gas of particles. Okay, and in one case, a fluid picture is useful. In other case, the particle description is useful. Okay, so I'll explain this two different ways of doing hydrodynamics. Then I'll talk about, so there's a way to just write down these equations of hydrodynamics in a sort of purely phenomenological way without bothering about the microscopic origin. But then there are some problems which I'll discuss. Then I'll outline the microscopic derivation that we have. And basically, this follows an approach first, I think, developed by these people, Zubarev and Morozov, in this very nice review article in Physicae. Okay, so they were actually trying to derive hydrodynamics using this projector formalism, which I'll discuss. And so I'll just give an outline of our derivation, and I'll discuss some of the main results. Okay, so the main idea of hydrodynamics is to basically use a coarse-grained description, and this description uses the fields which correspond to conserved quantities in the system. Okay, so for an n-particle system, there will be a few conserved quantities, and one writes a coarse-grained description in terms of these fields. Or sometimes if there are broken symmetries, one uses these broken symmetry variables to write hydrodynamic equations. So the point is that because they are conserved and they are locally conserved, they evolve slowly. While all the other degrees of freedom which are not conserved, they evolve fast, and they kind of provide like a thermal reservoir for the slow degrees. Okay, so because of this, a lot of internal degrees within with internal degrees of freedom corresponding to each sort of coarse-grained description of the macroscopic fields. The internal degrees serve as like sources of dissipation and noise for the slow fields. Okay, so this is what I'll try to explain in the derivation. So hydrodynamics is useful both far from equilibrium. For example, if you want to describe water flowing through a pipe, but also in equilibrium. And in equilibrium, instead of writing the microscopic equations, you can write the hydrodynamic equations and extract useful information on equilibrium dynamical correlations. And these correlations, of course, contain information about scattering experiments and transport measurements. Okay. So hydrodynamics is used in both, like in different situations. Okay. So basically, this is the basic idea. So we'll look at just one-dimensional system. So let's say I have this chain of particles or a gas of particles marked by these small dots. And the microscopic description is that each particle has a position and a momentum Q and Pn in particles. And the macroscopic description is like I divide the box into, let's say, small boxes of size L. So this L is kind of large in the sense it contains large number of particles, but it's not of the is much small compared to the full system size. Okay, so it might how large is of course not always very clear, but it could be even like 100 particles might be large. Okay. So the full system of course has like 10 to the power maybe 10 particles. So 100 or 1000 is already quite large. Okay, so now the macroscopic description is basically I divide this system into this boxes of size L, and in each box I define these fields, which are, let's say, I count the total number of particles in this box and divide by the length, and that gives me the density in this at this point. So X is now like a macroscopic variable, which changes from one box to another box in units of L. And so I count the number of particles in this box, the total momentum of the of all the particles in this box, and the total energy of all the particles in this box. Okay. So then I now have a field. So in each box I have these three densities, and then I can describe a slowly varying field over the entire system. Okay, so now what are the fields I'll consider depend on the conserved quantities. And we know that these are the variables which are used for describing the thermodynamics of the system, because they correspond to conserved quantities. And similarly for the non-equilibrium state or hydrodynamics, these are the relevant variables. Okay, so we just need to look at what are the conserved quantities in the system. Okay, so we have these three fields, and the question is, at the microscopic level, we have Newton's equations of motion for the particles, and we want to know what are the equations for these conserved fields. Right. So these three fields, what are the equation? What is the dynamics? Okay, and how do we go from this microscopic to macroscopic description? Okay, so this it is an important notion, the microstate of a system versus a macrostate. And each macrostate will correspond to a large number of microstates. Okay, so that is a important idea. Okay, so now let me just tell you what the standard hydrodynamic equations describing these three fields are, which is already known. So this is basically so there's number density, momentum density, and energy density, three basic fields. One can define other fields, for example, a velocity field U, which is just defined in terms of the momentum field, and energy per particle corresponding to the total energy density. Okay, and they satisfy basically this basically 1D and Navier-Stokes equations. So the first gives conservation of dense particles. The second equation corresponds to conservation of momentum, and the third equation is conservation of energy. Okay, and the structure of this hydrodynamic equations typically is that so there are there are two kinds of terms. These three terms are what are known as Euler terms, And then there are these other terms which involve, like this eta is a viscosity and kappa is a thermal conductivity of the material. Okay, so these are called dissipative terms. So these are the two. This is the structure of usual hydrodynamic equations. There are so-called Euler terms, and there are this dissipative terms. Okay. And in the Euler terms, what you see is that, okay, so this so there's a pressure term and there's a temperature term, and these are all defined can be obtained from the three basic fields that I defined earlier. Okay, so the energy density can be written as so you have to, if you subtract the flow, the energy due to the flow, which is just the kinetic energy of the center of mass, then what you get the internal energy, and the internal energy of the system is some state function. Okay, so if you know the density and temperature, you know the energy density. Similarly, the pressure is given in terms of rho and T. Okay, so basically I can think of I can write this equation in terms of just three fields which I can choose. So for example, I can choose density, velocity field, and temperature as the independent fields. And like I said, these equations will tell us how water flows through a tube, or if I if I have free expansion of a gas, how does the profile change, evolve with time. So these equations have this kind of information. Okay, so the basic structure of these equations is they are in the form of continuity equations. And for the three conserved quantities, there are three currents, and these currents have irreversible Euler terms and irreversible dissipative parts. Okay, so so here dissipation really means it's
Abhishek,
yeah.
Abhishek, Shyam here, I have a question. Just go back to the previous slide. One slide. Yeah, so it's noticeable that the dissipative term in the energy equation involving U del U by del X has the same coefficient as that in the momentum equation involving del U by del X. So there is the same parameter eta, viscosity appears in the three. Now, is that is there a symmetry that dictates that, or can those two coefficients be different? Because one of them, of course,
they have to be the same.
Work. So I think they are the same, right?
Yeah, they have to be the same, right? Yeah.
But it's not an obvious. It's not immediately interpretable as an Onzaga symmetry. That's why I'm trying to figure out what symmetry it is, or is it that somehow one can pull out the
right? Yeah,
I'm just. I suddenly realized that I mean, I hadn't thought about this before, but the fact that exactly the same coefficient appears there is independent of description, right? There is some fundamental reason. So if it's not a symmetry, then perhaps it's because, I don't know. I'm confused. Okay, I just thought I'd ask you. I thought maybe you knew the answer.
Yeah, I mean, I can't say immediately, but I think if I write the entropy production, the structure of this has to be this, like from the positivity.
Has to be that, right? Yeah.
Right, yeah.
Yeah, because it's coming from the dissipative work done by viscosity. It's coming from the power dissipated by viscosity.
Yeah,
so somehow it has to be the same. It's just that.
Right, yeah.
Okay.
Yeah.
Higa, so go ahead. I'll think about it.
I'll check and let you know later. I mean.
Hello, Abhishek, if I may. I suspect the symmetry here is probably Gaussian invariance or something. I'm not sure.
Also right, yeah, that's also true. I think it maybe just also can be shown from
maybe it's Gaussian invariance. It must be, I guess. Okay.
Yeah. Right. Yeah.
Yeah, probably. Okay. Yeah.
Yeah, Abhishek, I had a question. In the first, this microscopic description in terms of Hamiltonian variables, pure mechanics, and now you have entities like the temperature, which are thermodynamic in nature.
Yeah.
How did that transition happen? Like, I mean, did you have to define an entropy and at some point?
So I think in the derivation it will emerge automatically. The entropy somehow will just come out. Right. Yeah. I think maybe once you look at the way we derive things, it will just emerge automatically.
Okay, carry on. Yeah.
Right, yeah.
Abhishek, the one last question. So when you are writing this, you are doing some small fluctuation expansion, right? In general, there would be even higher order terms in U.
No, hydrodynamics, I mean, this is supposed to be complete, right? If it's supposed to be like even far from equilibrium, this is supposed to be valid.
But
So it's not even small fluctuations
current,
around equilibrium.
when you write down the current, could there be like U cubed term, third order term, or U to the power 4 term?
Sorry, I didn't, there's a lot of noise.
So maybe, maybe other people can mute their microphones.
Yeah, there's some microphone which is, okay.
Yeah, thanks.
Yeah, Sridip, can you repeat your?
Yes, so what I wanted to ask that when you wrote down the equation in the previous slide, so then the current in general could be, so you have only terms up to quadratic in U.
Yeah, but this is completely, this is, yeah, here there's no, I mean, I think it's more or less exact. You wouldn't get higher order in
You're
U.
saying that there are no higher order terms and
Right, yeah.
Okay.
I mean, when you like, of course, this you. I mean, when we do fluctuating hydrodynamics, you expand this around the equilibrium values, and then you stop at second order.
Yeah, but then
here it already includes those all. I mean, it's at all orders, right? It's not an expansion.
Yeah, one point. So when you define these independent fields, you have density, momentum, and temperature, right? Density, so instead of density, momentum, and energy.
Right. Yeah.
Yeah, I think that's all. That also, this kind of structure also comes up in when you look at these projection operators. Turns out that if you want to get an orthonormal set, then temperature is relevant rather than energy.
But that's here I could use any three fields. I mean, like I can use rho, u, and epsilon also. That's also fine.
Okay.
Right, yeah. Okay. So yeah. So let me continue. Okay. So
just one question, please.
Yeah.
Why are we saying about slowly varying fields? What happens if we do the same for fast, quickly varying fields?
No, I'm saying see, like the hydrodynamic equations are written for conserved quantities, and because they are conserved, they evolve slowly. I mean, so it just, I mean, this is what happens. Right? I mean, see, at a microscopic level, of course, atoms are moving and everything is very fast. But these fields are, because they are conserved locally, so they can only change, let's say, they have to change slowly. Because whatever goes down someplace has to leak out from the boundaries, right? So things can't change drastically. And so if it was not conserved, then things can just change very fast. But because, yeah, so that's just the statement. Of course, I mean, yeah. Okay. So, yeah, so dissipation here refers to transfer of energy from the hydrodynamic field to the internal degree. Okay. So there's no. So.
Hello.
Yeah.
Okay, now it's fine. I guess you can continue.
Okay. Okay, so dissipation, I mean, one should remember that this is a completely conservative system, and energy, particles, everything is momentum. It's finally totally it's conserved. So now the connection to microscopic is, one is that we need this equation of state and the internal energies, which are given by equilibrium statistical physics. And then there are these transport coefficients, eta and kappa. And these are usually given by linear response theory, which in terms of so-called Green-Kubo formulas. Okay. So this is the connection with the microscopics of the hydrodynamic equations. Okay, so so now what is fluctuating hydrodynamics? So fluctuating hydrodynamics is using the hydrodynamics in systems that are kind of close to equilibrium to describe fluctuations in equilibrium. Okay, so you can imagine a system in equilibrium, the fields are more or less constant, but then there are fluctuations all the time. And the question is like, how do we understand the properties of these fluctuations? And what you can do is you can take the hydrodynamic equations and add noise terms in the equations and make them kind of like Langevin equations. Okay, so there's a deterministic part, there's a dissipation part, and now you add noise to the equations. And the noise parts also have to be conservative. So I write them in this form of like a derivative of some noise. So this Z, E and ZE are the two noise terms in the momentum and energy equations. Okay, so typically the first equation, people don't put noise because this is supposed to be exact. Okay, and so the important point is that the noise terms also appear in this conservative form. It's like a derivative divergence of some object. Okay,
just one small comment.
Yeah.
The first equation is actually identity, so the option of putting a noise in it doesn't arise, right? If you write down a microscopic definition of the velocity field and the density field, then there isn't an option of putting diffusion and noise in the first equation.
Yeah, so that's why I said like, I mean, it's supposed to be exact in some sense.
Yeah, and the second comment I wanted to make is that, no, I just wanted to make one more comment, which is that the noise can be viewed not as something additional, but after all, if you take your original hand-drawn picture of 2 or 3 slides ago, you are using finite coarse-graining volumes to define these fields. Therefore, intrinsically, there are fluctuations in any quantity in those regions of order 1 by root little l, right? So the variables you define are averages over those finite volumes. You're doing finite, they obey finite system thermodynamics. So in some sense, your last terms in purple aren't optional, they're actually mandatory. If you write these as
that's correct, But so I guess in so I guess in when we study like typical out of equilibrium problems, then you don't really care about the noise terms, right? But if you want to study fluctuation equilibrium, then it's then that they really appear.
No, I mean, I think even in the out of equilibrium you could, but often in out of equilibrium you impose a non-trivial initial condition and you watch the evolution of the mean quantities. But even there you could care about the fluctuations.
Right, yeah. But typically you expect that they shouldn't do much, right?
Depends on the problem, I would say.
Okay, yeah. I mean, in principle,
but I go ahead.
Yeah, no, this of course I completely agree that these terms will emerge automatically, as we will see in the derivation. I mean, so they are of course there because I mean, if you have dissipation, fluctuations will emerge automatically. Right? Okay, so but typically you put this phenomenologically, and then what you impose is that the noise and dissipation should satisfy some sort of a fluctuation dissipation relation, which ensures the system stays in thermal equilibrium. Okay. And
Abhishek, hi, like I had one question, like these dissipative parts, this eta and kappa part, these are also added phenomenologically, right?
I mean, yeah, so initially, of course, when it was written, like, I mean, Euler wrote the equation without these terms, and then Navier and Stokes added these terms just by observations of what you see in experiments. Okay. And
so I was wondering, like, are there I think we are making some assumption about the linearity. That's why, like, it's up to linear in U that Trijit was asking.
No, so he was asking about the Euler terms, the forms. I mean, whether they are exact or right.
Okay.
But, the dissipative terms are typically taken as linear, and yeah, this we'll just find. I mean, like when we do the derivation. So of course, people have earlier done microscopic derivations of hydrodynamics starting from the Hamiltonian, and these terms emerge, and that's how you get the Green-Kubo. But that process is kind of like, it involves a lot of approximations and assumptions. And so right now what we are trying to do is a different way of doing the same derivation. Yeah, so
can I ask a question?
Yeah.
Abhishek, the Deepak, I think, has a question in the chat.
Where is the chat? Okay, I guess Sriram maybe answered the question.
Yeah, can I ask a question?
Yeah, I think Sriram sort of answered the question.
Hi, can I ask a question?
Yeah.
Yeah, so could you motivate a bit this form of the psi p and psi e? Why do they appear with one derivative and so on?
Okay, so one derivative, because it has to be conservative, so you put a derivative. So it has to be so like I see they always have to have this sort of a continuity equation form. Okay, and this JP, now you can put a noise term there. So then you basically get this form. Is that okay?
Yeah, so you think of psi p, size as addition to noise addition to the currents.
Right, yeah.
Yeah, okay, thanks.
Yeah. Okay, and so they have to satisfy this fluctuation dissipation term. So yeah, so the question again,
sorry. So is there a way you can say that at the same order of relevance, you need not add higher derivatives, or like in what sense it's suffices to like work with one noise fields which are a single derivative or something?
I think if you like, I mean, okay, so in some sense, this is the simplest thing that will work. Like, okay, so you want to add a noise term which has to satisfy this fluctuation dissipation property, and given the structure of the dissipation, so okay, so fluctuation dissipation means the noise and the dissipation dissipative terms have to be related in a certain way. Okay, so given the structure of the dissipation term, if you want to write something in the noise which satisfies fluctuation dissipation, I mean, you are pretty much constrained to add something like this.
So at least that is kind of given in as an input. Is that right?
So the fact that it has to satisfy fluctuation dissipation, because you want your fluid to be in equilibrium, right? Whatever you do, you know as a fact that it will always go to equilibrium. So so it has to be like this.
Okay, thanks.
Right, yeah. Okay, so so again, Deepak's question again, like sound. So his question was like, I mean, sound of course can move fast, but I think again one has to look at like what does fast really mean? I mean, so like comparing which like scales. So this is one has to do it carefully, but maybe I won't discuss this too much. Okay, so yeah, so this is about fluctuating hydrodynamics. Okay, so now I mentioned right at the beginning that there were two versions of hydrodynamics, a lattice version and a fluid version. So far I've been talking about the fluid version, and the lattice version is like it's useful for describing things like anharmonic chains, which in one dimension, of course, the distinction between a crystal and, because you don't have a crystal, so everything is a fluid. But somehow, if you take an anharmonic chain like this Fermi-Pascular Singham model, it's a different description is sometimes useful. Where so here now you, instead of thinking of x as the position in space, you think of x as the it's like fixed on the particle. It's a particle index. Okay, and then you go on to identify the three conserved fields. So the first field is typically taken as it's like the distance between two particles, which is like inverse of density. Okay, so instead of density, we look at this extension field Rn, and then the other two fields are momentum and energy. But this n index is like the momentum of the nth particle, and En is the energy of the nth particle. Okay, so this is the total energy of your Fermi-Pascular chain with the kinetic and potential energy. And each, I mean, you can think of it as the sum of n particles energy. So epsilon n is just this energy. Okay, so these are the conserved quantities, and typically if you take a non-integrable system, these are the only conserved quantities, and these are now the fields. Okay, so instead of x is now like moves with the particles. Okay, so that's the main difference. So using this description, again you can write hydrodynamic equations, and in this case they have this particular form. So if you look at Rn, I mean, if you take a derivative, it's just Qn plus 1 dot minus Qn, which is basically like divergence of momentum. Okay, so that's almost the first equation. And similarly, the second two equations. So these are the Euler terms. This is the Euler part. So the stretch current has the stretch field has momentum as the conserved current, and the momentum field has pressure as the current, and the energy field has pressure times momentum. Okay, so that's the current corresponding to energy. So these are the Euler terms, and then these are what one writes purely phenomenologically as the dissipative parts. Again, these look like these are linear parts, and they have this very similar structure what we saw the viscosity and heat conduction terms, right? And then you add noise terms again only in the last two equations, because the first equation looks like it's more or less exact. Yeah.
Hi, Asaf Miran from the Weizmann Institute. Just a quick question about your last equation.
Yeah.
It seems that in the previous set of equations, in the dissipative terms, you had the, say, the gradient of the momentum, whereas here you have the gradient of the stretch or the extension. Can you comment on that?
Can you repeat again?
Sure. I'm saying in the last equation, in the dissipative terms, you have two dissipative terms. One.
Okay. You're asking why this doesn't in the previous case this involved P.
Right. Exactly. That's the question.
And here it involves R. Okay. So. Okay, so there's a detailed reason which is so I'm writing these equations as given in so this was first written by Herbert Spohn, and he had some detailed arguments of what the form of the dissipation matrix should be, and I'm just writing it down. So there's a I mean what he uses is some symmetry arguments. Basically time reversal invariance, which using which he argues what the structure of the dissipation matrix should be for this particular model, and it just turns out to be this. Okay, so I mean, yeah, this is an interesting question why it looks so different, because I mean doing some transformations actually you can take this to the fluid equations, and I've not done this, but I mean if you do this, I mean you should get back what I wrote for the fluids, but yeah, right now I mean
Abhishek.
Yeah.
Just a comment.
Thank you.
As far as time reversal goes, both the term you have here and the term in the previous one have the correct time reversal signature, because that one has two factors of U. So there's no dispute that both terms are dissipative terms because they have the opposite time reversal signature to the d by dt term. There's no problem there. The interesting thing about the term in your Fermi pasta, in your FPUT chain, is that it is linear in R, whereas in the earlier version, you had to write something non-linear in U. So
no,
it's as though you will be able, right?
Okay.
The time reversal signature is fine. That one has got a U squared, so it's even. It's got two factors of U, so it's even. So there's no dispute about the time reversal character of both terms.
Right,
the interesting thing is one of them has U twice over, and the other one just has R. And the term which just has R, you might be able to get from linear irreversible thermodynamics without too much trouble. So it has that nice feature, the Spohn version.
Right, yeah.
Right? Suggests that you can get a dissipative piece of the energy current from gradients of the extension. So you could argue for it in linear irreversible thermodynamics, whereas the other one is a little trickier, even though it's more conventional.
Right. Yeah.
Anyway, so I won't interrupt.
Right. Okay. Yeah. So right. Yeah. So I mean, yeah. So many of these things are still like kind of subtle and not completely clear. Okay, so yeah, so this is what is kind of written is standard form of the equations, and so these are the Euler currents. There are three currents, and P is the pressure.
Abhishek, I had a comment to make.
Yeah.
In reply to Sriram's question, the two viscosity terms, eta, the equality of those two, it may follow from Galilean invariance.
Right, yeah, I think someone else also said, maybe Loga said that, I guess.
No, in the comments, I put it up on the comments. It might be the answer to this question.
Right, yeah, I think it follows from Galilean invariance, right, yeah, that's true. Okay, yeah. So,
there's a question in the chat box also by Sujit, and he's asking, what is the form of chi here? What kind of noise are they?
Okay. So the noise is so it's a function of x and t, and it's delta correlated in both space and time. And the correlations are the noise correlation is related to the dissipation matrix, which involves this dp, de, and de tilde. Right. Okay. So I hope that answers. I'll just check if there are other questions.
Here, instead of viscosity, you are encountering diffusion like effects, right?
Yeah, but it's basically the same. I mean, these are like the viscosity. I mean, in some sense, these are the dP is the viscosity, and dE is kind of like the heat conduction term. Right. Okay. So So again, this pressure is given by the equation of state in and in this model, you can find the equation of state can be found kind of numerically, and the noise is of course related by FTT. Okay. So some comments on this lattice hydrodynamic equation. So. Okay, so again, I just want to introduce some notation. So there are three conserved quantities, and I'll introduce this field vector Ux, which consists of the stretch field, momentum field, and energy field at different points x. And so these are the three, and the corresponding currents are denoted by JAX. Okay, so A is the field index and X is the space index. Okay. And then the hydrodynamic equations have this structure that del Tu Ax is divergence of some current, and there's an Euler term JAX, and then there's a dissipation term, and then there's noise. Okay, and so this I have written more generally, like you can have more number of fields and so on. And this noise strength. So here I've taken out the noise strength. So zeta is a noise with unit variance, delta correlated both in space and time, and the strength of the noise satisfies this fluctuation dissipation relation. So BB transpose is CD plus D transpose C, where D is the diffusion matrix and C is the equilibrium correlation matrix in the system. Okay, so this is basically the statement of fluctuation dissipation, and so this C out here is the correlation, if you is the correlation matrix of these fields. Okay, so it's basically a 3x3 matrix, C, and similarly D, and the equilibrium distribution is basically then given at the Gaussian level. If you just so in equilibrium I have this hydrodynamic fields, and then there are fluctuations, and at the if I just look at Gaussian fluctuations, then the distribution of the fields is given by this equilibrium measure. Okay, so
I have a question for you.
Yeah.
Is it possible to derive that this noise is delta function correlated or equivalently that the probability distribution is Gaussian? Why can't it be more nonlinear than that? Examples in which this happens actually in this work of Loganayagam and all our students, they are getting probability distributions which are cubic also, not necessarily quadratic. So is there some assumption you're making in this derivation?
Right, yeah. So in the derivation, actually, we will make something called, we will make a Markovian approximation, which makes it local in time. And then there's also approximation where we assume that the system has very short range correlations, and so it spatially also it becomes like delta correlated in some sense, right? Yeah. But at some stage you'll see that the Langevin equation probably has like special long range correlations, which if you but eventually we want to bring it down to this kind of simpler form with delta correlations.
Okay, all right, thanks.
And because if the noise was correlated, already it's very difficult. If the noise is correlated, then of course it's much more difficult. And physically, we expect that, just like when we write a usual Langevin equation, we expect that somehow, even though it's, in principle, there's always correlations in time, but it's making the Markov approximation is usually quite good, and of course very useful. Okay, so these are the equations of fluctuating hydrodynamics, and they have actually provided a basis for understanding anomalous transport for a large class of one-dimensional systems. Not just anharmonic change, but really a very wide class of systems in one dimension. And this is a lot of work done by Herbert Spohn, and this was first actually proposed by Sriram and Anuttam. That you can use fluctuating hydrodynamics to understand anomalous transport, and then Beijeren had some work, and then Spohn really developed a very into a detailed structure for this theory, including connections to things like KPZ and Levy distributions and so on. So this is like how you use fluctuating hydrodynamics to understand equilibrium problems. You can also, without the noise and dissipation terms, you have the Euler equations, and this you can use to study, for example, shock propagation in a one-dimensional gas. So this is called the Riemann problem. You take some front, there's a discontinued front, and how does it evolve in time? Okay, so this is the Riemann problem, and you can use the same equations to understand such problems. Okay, so now the connection to microscopic of this lattice hydrodynamics is again you need to use the equations of state, and then the question about Bayer transport coefficients is the problematic one. So the problems with the theory is that one of the problems is that if you use a standard Green-Kubo formula to find to compute these transport coefficients. So DAA is what I will call the transport coefficients. They are like viscosity and heat conductivity. So in this case, it turns out that you get divergent answers. Okay, so these Bayer transport coefficients blow up if you use standard Green-Kubo formula. Okay, so a second problem is that the fluctuation dissipation theorem ensures a steady state only at the level of Gaussian fluctuations. So, so this current, of course, is nonlinear, but if you look at if you expand it to linear order, then this Langevin equation is made in such a way that it leads to equilibrium. But if you include the full nonlinear terms, then it's not guaranteed, and you have to put additional conditions on the equations, which is not very satisfactory. Okay, and finally, this theory does not explain some of the recent numerical observations in non-anomalous transport. So this is some technical thing which I want to maybe detail. Okay, so it's good to have a microscopic derivation of this.
Abhishek, question.
Yeah.
Actually, when you write down fluctuating hydrodynamic equations, the input is some effective free energy functional for the slow fields, and you can and that effective free energy functional by no means has to be only quadratic in the slow fields. You can certainly, the general prescription for writing down these equations guarantees the correct steady state, quite independent of whether that steady state is Gaussian or not. The agreement between noise strength and Bayer damping takes care of that. So I wouldn't agree that maybe for this particular problem, for this particular formulation, there is some such constraint. I don't know. But in general, you have slow variables. You have a prescribed effective Hamiltonian for those slow variables. And you write down an equation where noise and damping stand in the standard relation of noise covariance is equal to damping matrix times temperature. And that part is all right. So I don't know. And also the divergent estimates for the transport coefficients are a physical result, right? Is that the actual renormalized transport coefficients are singular.
No, but that's the renormalized transport, not the Bayer transport coefficients, right? Because in the hydrodynamic equations, what you have are the Bayer transport coefficients.
Yeah, but what you calculate from the Green-Kubo formula are not the Bayer transport coefficients.
But I mean, if you look at the standard derivation, what it will give you the usual Green-Kubo formula, right, for this Bayer transport coefficients.
No, it doesn't give. No, I mean, so okay, we can fight about this later.
Right. Yeah. But the main point is there's no formula for currently there's no formula for this D from the microscopic Hamiltonian.
For the Bayer transport coefficient.
Right. Yeah. For the Bayer.
For the Bayer ones.
Right. Yeah.
Yeah, that I agree. Yeah.
Right, yeah. So that of course is not satisfactory, and so there's need for a microscopic derivation. And so anyway, of course, independent of anything, it's always good to have a microscopic derivation because it's the same system, and you want to understand how everything in this is related to the original Hamiltonian, right? So that's a basic.
The divergence that you're talking about, is this the kind of thing that you see in mode coupling theory with the long time tails emerging, or what is the divergence that you're talking about?
Yeah, so the calculation is done using mode coupling theory, for example, and then you find that, but that of course usually is for the renormalized diffusion constant. But if, for the basic, for the Bayer transport coefficients, also if you just compute the usual, if you use the usual Green-Kubo, you will get a divergent answer. I mean, you can use mode coupling theory to do the computation.
Mode coupling is usually used for the renormalized one, but
right, yeah. So,
even at the Bayer level, there is a divergence.
Right, yeah. Right. Okay. So, so therefore, we would like to have a microscopic derivation. Okay. So the main. Let me now come to the derivation of the equations. So the main steps are one has to use a specially coarse-grained variables, of course, and the idea is that the microstate evolves via deterministic Liouville equation, and then what we'll do is we'll use the projector technique to split the evolution of the macrostate into a slow Euler part and a fast fluctuation dissipation part. Okay, and right, and so it's clear why that the macrostate actually evolves stochastically, because each macrostate corresponds to like inside it can be anything, right? So a given macrostate corresponds to, like, within each cell L, I have specified the number of particles, momentum, and energy. But inside I can arrange in I can have large number of microstates. And if I just look at the macrostate, then I can't exactly say how it's going to evolve. So it has to be a stochastic evolution, and I can. So that's why I get a Langevin equation for its evolution. Now, in the derivation, it's useful to get so corresponding to a Langevin, one can always write a Fokker-Planck. Now, in this microscopic derivation, it's useful to actually first get the Fokker-Planck equation. Okay. And from that, once you have the Fokker-Planck equation, you can read off the Langevin equation. So this is the strategy. Okay, so this is the Langevin equation I already wrote. This is the Langevin equation that we finally want to have. Now, corresponding to this, the Fokker-Planck equation is, so that would be an equation for the distribution of this field. Okay, so I have a field U which can take, which is stochastically evolving, and I can ask what is the distribution, and I denote it by this function f. Okay, so this is the distribution of the field, and this is the Fokker-Planck equation corresponding to this Langevin equation. Okay. So, so typically, if you have a Langevin equation, there's a drift term and a noise term, and the drift term gives rise to this this part of the equation, and the noise part gives rise to this kind of a second derivative in the field structure. Okay. So this is the equation that we finally want to derive. Okay, so I'll just wait for, if there are any questions, I'll wait for 5 seconds.
I have a question. It's the question which Tribid had asked before, actually. I didn't quite understand your answer. I mean, the hydrodynamic equations you're doing should be consistent with Galilean relativity. So the currents should have some sort of a derivative expansion in general. I can write down lots of terms, actually, which are consistent with Galilean relativity. Why did you say that those equations that you wrote are unique? And they are not an expansion. They're not a derivative expansion, you said. Why? That I don't understand, actually. I mean, there are other reasons to believe from ADS-CFT correspondence why, in general, you'll have a derivative expansion. But I just wanted to raise this question. You said it's exact, you know, I mean, it has to come out.
Like the Euler equations, I mean, they are exact at the Euler scale, right? So, I mean, in,
no, I'm talking about the dissipative terms.
The dissipative term, no, okay. So, of course, I can have higher order terms, but I mean, is that what you're asking? Like, why do I stop at second order?
Yeah, exactly. You can have higher derivative terms. More complicated terms, but they are suppressed by some scale of the system.
Okay, maybe Sriram can answer that.
No, I think it's what Abhishek just said, that, and it's, I think both of you are saying the same thing. The dissipative terms here are written to the leading order in the gradient expansion at which such terms appear. Because of momentum conservation, the terms you have there are the usual viscosity, etc., are the leading order dissipative terms in a gradient expansion. In principle, you can have higher orders, and indeed, they are suppressed by scale, etc. So I think that's all it is.
But therefore, he should, in the derivation that you present, you will be seeing those approximations, derivative expansion.
Yeah, in principle, if you like, I mean, one can imagine that there'll be, but I think under some scaling, they should go away. So, I mean, like there's this length scale L, which I've introduced, and then I have to do expansions in that using that length scale, and it's my feeling that under some
scaling limit of time and space, if you scale appropriately, this I think is right.
Yeah.
Okay, thanks. I didn't want to hold you up.
Abhishek, if I may comment a bit on this question. So, you know, in the case of this hydrodynamics of stochastic particle systems, whether with single conserved quantities like SEP or KMP, you can derive fluctuating hydrodynamics with the dissipative terms which are higher orders. And then you make an assumption that you would only look at small fluctuations. And they would be correct as long as you want to look only the 2-point correlations. But if you want to look at higher point correlations, then you need to take the higher order terms. So essentially what you are doing again this derivative expansion around a very slow moving modes. And they are usually, for, if you can see that they would give you this correct result for 2-point correlations.
Right. Yeah, but yeah, I mean, somehow I can't imagine for example, basically we are asking in Navier-Stokes equation, can I have higher order derivatives? Yeah, somehow it looks very unlikely. I mean, I can't give a reason, but yeah, I mean, somehow I feel that it should go away under some scaling, at least for fluid systems.
Okay, thanks.
No, I mean, it's Abhishek.
Yeah.
In principle, you can have terms with, let us say, 4 derivatives instead of 2, which are called, I mean, they have some super Burnett or something. They all come with prefactors, which are powers of the mean free path. So if you look at length scale large compared to the mean free path, those terms don't matter. It's the usual, I mean, that is the parameter that sorts what scale you are at, right? And so in principle, if you're doing gas dynamics or something, and you're looking at the air in a computer hard drive between the drive and the wall, you can actually be at length scales below the mean free path, and you could have to worry about that. But in a long wavelength theory, you will not worry about it. I really think that's all there is to it. And you are implicitly looking at leading order in such an expansion.
Right. Yeah. So I think that's in the in the scale we are working. I think it should just go away. Right. Yeah. Right. Okay. So yeah. So maybe I'll then proceed. Okay. So now we want to start with the Liouville equation and somehow arrive at this Fokker-Planck equation. Okay, so again, some notation. So this is our system of particles, and so the microscopic description is like I have this stretch variable, momentum, and energy variable at, and these are local variables. Okay, so the C indicates local variables, and then I define like the total. Okay, so these are the kind of the densities. I sum up all the C's and divide by the length, and this forms my coarse-grained variables. Okay, so this U hat, A stands for the 3 fields, and X is the space coordinate. But space now means this is X equal 1, and this is X equal to 2, and so on. Okay, these different cells. And similarly, I have a local current for each cell. Okay, and the microscopic evolution, because they are conserved quantities, one can check that if I just take a time derivative of the fields and use the equations of motion or just the Poisson bracket, then I get divergence of the some current. Okay, so that defines my current operator, and these are now phase space variables. Okay, so whenever there's a hat, it means it's a phase space variable. If there's no hat, it's a C number. Okay, so that's this notation. Okay, now, so then we have a macrostate, which is given by the set of UAX. These are C numbers, and it corresponds to a large number of microstates, and that's why we say that evolution is not deterministic. So at time t equal to 0, let's say rho hat
Abhishek? Yeah. Sorry, I had a quick clarification. So always you're thinking about systems with short range interaction between the underlying microscopic degrees of freedom?
Yeah.
Okay, thanks.
Right. Yeah, that's important. I mean, okay, so of course, so far, yeah, I think that's of course completely necessary. Yeah. Okay, so at time t equal to 0, so rho hat, so for a given macrostate UAX, I can have a large ensemble of microstates, and this I denote by this density phase space density rho hat. Okay. Okay, so these are like different microscopic conditions which will all give the same macrostate UAX. Now, this ensemble rho hat will evolve via just the Liouville equation, which is a deterministic equation. And then at a later time, basically, this rho hat will, because there were many microscopic configurations, this rho hat at a later time will correspond to a possible different set of macrostates, right? So we can ask what's the distribution of the macrostate corresponding to a given microscopic ensemble. And so let's define this object. So given the phase space density and what is the distribution of a given profile of the macrostate. Okay, so so this is then the distribution. Okay, and now we want a Fokker-Planck equation for this object, for the distribution of the U. Okay, so if we take a time derivative of this object, then basically what you can do is, so you get del T of rho, and del T of rho is basically given by L of rho. The L is the Liouville operator, and then L of rho, you can take it to this side. You can just do a partial integration and bring it to this side, and that is like del T of this object, and this gives you basically when you take time derivative of the conserved quantity, that gives you divergence of a current, right? Okay, so and then you have this partial derivative with respect to the field. So that's just a trivial step. Okay, so this is the basic idea of the derivation. You given a microstate described by rho hat, I define a distribution f and I ask how the distribution evolves, and I get a structure like this. Okay, so now this rho hat, I want to break it up into slow part and the fast part, corresponding to the two conserved and non-conserved parts. And here is the projector operator formalism is kind of useful. And basically what I have to do is I define an operator P, which acting on any function of phase space variables, it projects it to the three conserved fields. Okay, so so this basically means that I look at all configurations in phase space which correspond to the same same profile, macrostate profile. Okay, and I integrate over all those microstates with the correct weight, and this is how I define the projection. Okay, and here rho hat is kind of the kind of like a local entropy function. Okay, so now I in this previous equation I break up rho hat into I project it into the conserved quantities and the non-conserved part. Okay, so Q is just 1 minus P, and this is projection into the slow fields, and this is projection into the fast fields. Okay, so okay, so now if I so basically I have this equation and I write rho hat as P rho plus Q rho, right? If I look at what P rho gives me, it gives me precisely the Euler term in my equation of equation, the hydrodynamic equations. Okay, so I just show how this kind of quickly go through this. I mean, it's not important to follow all the details, but the basic structure of the proof. Okay, so so I look at just this part. So there's P rho hat, and then I define use this definition of the projector, and so this is the projector, and then I just do some manipulations, and there's no approximations here. And what you can show is that this you can write it as this object, which is again F, and this object, which is the expectation of divergence of J in this microcanonical ensemble. Okay, so this is a local microcanonical ensemble, basically defined by this object. Okay, but with U hat replaced by a C number field. Okay, so that defines a local. So you can just imagine I have a slowly varying field, and in each region the system is kind of in local equilibrium. And I define my current expectation using this local microcanonical ensemble. Okay, so so this term now, so basically I took time derivative of the distribution of function, and I got two terms which has a P and Q, and the term corresponding to P gave me this. Okay, and this, if you look at, if you go back, this is basically this this part of the equation. Okay, so this is exactly the Euler term in the Langevin equation. Okay, so the so using this projector approach, you can quickly get the Euler term immediately, and then this part is the sort of more tricky part, and this I won't go through the details, and so this involves a lot of manipulations, and here you have to make the Markov approximation, and Markov approximation basically means like you get some terms like maybe e to the power L t minus s into f of s, and you replace f of s by f of t. Okay, so this is like typically what you would do, for example, if you are deriving the some quantum master equations or Langevin. I mean, this is the usual way you do the Markov approximation. And so this is kind of answers Spinta's question, like why it's delta correlated in time. I mean, this, but physically this, you expect that this should be a good approximation. Okay, so after doing all this, then this is the earlier part that we already had. This is the Euler part, and then you get this extra terms. Okay, and this, okay, so this, first of all, you notice that there are two derivatives in the fields, and there's space derivatives del x and del x prime. And in this derivation, of course, you don't get higher order terms. I mean, it just comes exactly like this. And okay, so this is the structure, and this this k's are given by some kind of like time-dependent correlation functions. Okay, so so this is Q. This is some projection on the current operators, another projection on the current operator, and then there's a time evolution. Okay, so it's some kind of like time-dependent correlation function, and you integrate it over this, and you get this transport coefficients. Okay, so right now it still doesn't have. So this is what we want. This is what the structure we were looking for. This we already got, and right now it you can see these terms, but it doesn't look like del x square, and this also is still not there, right? So it looks a bit different, but roughly it looks like our required Fokker-Planck equation. Okay, so here at this point, I just want to make some comments that first of all, in this form, you can check that. So if the system is in equilibrium, then if then what you can easily see is that the distribution should have this structure. Okay, so this omega u divided by omega equilibrium, and if you plug it in this equation, then you can show that this exactly vanishes, the right hand side. So therefore, in this at this level, the equilibrium state is an exact invariant measure for the Fokker-Planck. Okay, and what is interesting is that this Euler term and this term, they vanish independently and identically. Okay, so of course this is easy to see. If you put omega here, then it becomes a constant, so the derivative is 0. This part is more non-trivial to show that when you put f equal to omega by omega equilibrium, that this is exactly 0. But this just follows from conservation of phase space volume, because this is like an so S equal to k log omega is the thermodynamic entropy of the system, and this just says that the Euler term doesn't generate entropy. Okay, so the other important point is that also this equation is spatially non-local. Okay, so it involves both x and x prime derivatives, and this is also very different from what we are eventually going to, what we eventually want to get. Okay, so we could of course stop here and explore this equation, but we'll make some further approximations to get our desired structure of standard fluctuating hydrodynamics. And this approximation is, okay, so out here I have this operator. So this is the Liouville operator, but I used a projected version. And here one has to, I mean, to make some, if you make some physical arguments, what you can argue is that you can replace this Q by identity. So we replace it by this operator. And then we assume that spatial correlations decay very fast, so the equations become local. And then you use some standard ensemble equivalence between local and local microcanonical and local Gibbs. Okay, so at the end of the day, doing all this further approximations, we eventually get exactly what we wanted to get, the correct structure of the Fokker-Planck, and from that you can read of this particular Langevin equations. And then you find that the transport coefficients are precisely given in terms of, okay, so there's some structure here, but what is important is that this involves this correlation functions, which almost looks like Green-Kubo, but it's a bit different. Okay, so this is, you take the current operator, project it out to the fast degree. So you project out the slow evolution of the current, and then compute this correlation. Okay, and that essentially gives, so this is almost looks like Green-Kubo, but it's a bit different, and maybe I'll just explain the difference. Okay, so the usual Green-Kubo formula that one writes is, okay, so first of all, this X out here, it's the, remember this was like I made these blocks of size L, and X was defined at each block. Okay, the usual Green-Kubo formula would have like it's on the individual sites, and it looks the same, but it's defined on sites, and then there's a projector, and the projection is the same projection, and basically you project out the conserved quantities. Okay, so this is some standard form that you use in Green-Kubo. And the modified thing that we get is, the only difference that is there is that this instead of the local fields n, you use the coarse-grained variables x. Okay, and this makes a big difference. Okay, so I'll just show some numerical results of like if you use these equations. So there's a coarse-graining length L, and using that you have to use evaluate this quantity. So for the Fermi-Pascal chain, if you do a molecular dynamics simulation and compute these objects, then what you find is that if you use the standard Green-Kubo, then you find that the current correlation has this is this dotted line. It's a slowly ticking function, and the integral diverges. Okay, so here we plot the integral, and you can see that it has a divergence, and so there's a problem. But on using these coarse-grained variables with some length scale L, you find that they have this very fast decay, and as you make the length scale larger and larger, it converges to a nice quantity. Okay, so so therefore this we have this modified Green-Kubo formula gives you the Bayer transport coefficients completely, and there's with a nice prescription. Okay, what is the time? Okay, so maybe so I think I've basically come to the end. Okay, so basically this is a basic question that we are addressing. How do you go from Newton's equations to Navier-Stokes? And I presented this approach based on this projection operator formalism by Zuborev and Morozov, which is really nice. And it's so the other approach that is quite popularly used is, of course, it's you start with the so-called BBG-KY hierarchy, and you write the Boltzmann equation, and then the Boltzmann equation basically will give you can give you the hydrodynamic equations, and that also, of course, involves a lot of approximations and all, and at some stage it's not easy to see that what's the correct form of the transport coefficients here this approach gives actually slightly different form, which turns out in this case to be the correct one. Okay, and the Euler terms, of course, we see that it's exactly what was proposed earlier, and but the form of the dissipation matrix and the Green-Kubo formula are different, and divergences are avoided. Some other interesting open problems are, so we have got this diffusion constant, but can we verify this numeric independently in some other way? And then there's this question of transport in almost integrable systems, which is very strange and unexplained, which we want to use this now that we have a lot of more structure in the equations. We want to see if this can be explained. Then the use of this formalism to stochastic models with a finite number of conservation laws, example, anharmonic chains, exclusion process, and so on. So there's actually Anupam and some people at Weizmann. They had a different approach, which is valid for stochastic systems of, again, deriving fluctuating hydrodynamic equations. And I think it will be useful, nice to compare this approach with, because this approach in principle, it can be used even for stochastic systems. And that's a very interesting problem, how to compare what we get here with these other approaches. Then there's some recent work on generalized hydrodynamics where, again, this question of diffusion constants is interesting, and we think this can be applied. Finally, these equations also, like I said, can be are valid out of equilibrium hydrodynamics. And there, some, again, recent work at ICTS with Shubhadeep, Santosh, and Anupam, we find some very interesting results on where we compare microscopic evolution with macroscopic theory, and there are some interesting disagreements which might become clear once you understand the microscopic derivation better. So, okay, so thanks, and this is the reference for this work.
Approximation where you consider e to the power of minus q l that operator where you replace q by that one, e to the power minus q l t, and you replace it by e to the power minus l t. That means q is actually identity minus p. So you're basically ignoring that p l t.
Yeah, so here basically it's this, okay, so we don't have a rigorous but physically it basically means that, okay, of course this Q, this is acting on this object, so it's on the kind of fast variables, and the physical idea is that the slow variables are changing very slowly, okay, and compared to the fast variables. So even if I use the full evolution, the time scale on which the fast guys are changing, even with the changing, when the slow field is changing, it's changing so slowly that it doesn't affect the correlations so much. So that's the kind of physical idea. We have some, in our paper, we try to give some like sort of perturbative explanation for this, why this is valid. But it's, what was your question actually? I didn't.
That was basically it, like the justification for this.
Right, yeah.
Abhishek, just one question. So, is this possible to adapt this approach for the Toda chain? Is that what you have in mind?
So if you think of integrable models like this generalized hydrodynamics, there, also people have found that actually when you write the hydrodynamic equations, even though it's an integral system, you have dissipation terms. And then, of course, you want to write the dissipation using similar kind of Green-Kubo formula.
Right.
And but there also you run into the same problem, at least in some systems where you have divergences. And this might be a way to fix those divergences.
Okay. So with the Toda chain being one of the one,
right? Yeah.
Right. Yeah. Okay.
Right. Yeah.
Okay. Thanks.
Abhishek, I had a question. You said you calculate the air transport coefficients and relate them to a certain correlator of the fast part of the currents, right?
Yeah.
Correct?
Yeah.
And Baer by definition means evaluated at the local length scale little l, correct?
Right, yeah.
Right?
Yeah.
I didn't understand why. Yeah, if you take those quantities and you start evaluating them, now imagine changing the scale little l, right, which you do. Then shouldn't the transport coefficients that you measure at that nominally bare scale pick up fluctuation contributions from all scales below that, right? So that as you go to larger and larger values of small l, those should start to show the same kind of singular behavior as the physical transport coefficients, right? How do they escape that? I'm not understanding that.
No, so in some sense,
So
I'm
you have a
subtracting
system
of
that's
the.
that big.
So in some sense, I'm subtracting of the slow part, right?
I see.
This is exactly doing that, right? I'm subtracting
so
of the
somehow
slow
even. Part. I see. So.
So QG
your definition of slow is kept. So your definition of slow is. So I guess that's what I'm not understanding. I see your definition of slow is absolute and doesn't depend on the scale L. Your definition of slow doesn't depend on the scale L. Your definition of slow is absolute. It just depends on projected onto conserved quantities versus not projected onto conserved quantities. Is that right?
Right, yeah. But of course, the conserved
quantities so that's probably why.
The conserved quantities are constructed on the length scale L, so they of course depend on the length scale.
Okay. So I'm just confused. I mean, naively, I would think that if you just evaluated what is nominally a Baer transport constant, a coefficient, but you vary the coarse-graining scale, you vary this inner scale, your effective ultraviolet cutoff, and you make it a longer and longer length scale, somehow I would have thought you would pick up the normalization effects. But presumably, this is your way of defining the Baer transport coefficient somehow evades this. It looks like I'll have to read your paper to understand it. That's the only thing that's confusing me. If I just took a system specified by some stochastic PDE and now said I'm going to revise my ultraviolet cutoff and make it a larger length, then I will pick up some of what is nominally a fluctuation correction under that process. But you seem to have a process that somehow escapes this, and I haven't understood why, but perhaps it's best for me to just read in detail what you have done rather than bother you. So, Tika.
Right, yeah. So the current itself is still a local object, but what we are subtracting is in some sense, it just removes the slow part of the current, the hydrodynamic.
Okay. Okay, so I'll study your paper. I'll leave you.
So I would like to add a comment in this discussion. So I think if you try to compute equations for conserved quantities, so the currents for the conserved quantities will involve at some point with some non-conserved quantities. And those non-conserved quantities are anyway fast variables. As Sriram was saying that the difference between slow and fast is basically either they are conserved quantities or not conserved quantities. So is it that you're projecting out from projecting out from the conserved quantity space? Is it that the currents in the conserved quantities, those currents in the conserved quantities are coming from the non-conserved quantities? Is it that those currents you are taking it in the Green-Kubo formula? So the first part of the current of a conserved quantity equation comes from the non-conserved quantities?
Right, yeah. comes from the non-conserved. So I'm just keeping the non-conserved part of the current.
Yeah, so what I'm saying is that if you write down equations, yeah, so as you have mentioned our work with David, Asaf, they are in the audience, and we did similar work, but for a stochastic model, although there are some Hamiltonian parts also, but very simple. And in that case, our derivations are in many places similar, although we had used stochastic properties, but in many cases are similar, and we actually saw that the currents, the contribution to the currents which are coming from the non-conserved quantities actually contribute to the dissipation of the conserved quantities. So I think the similar things are happening. You are doing it more systematically. You are projecting out the current to the space which out of the conserved quantity space, I guess.
Right. Yeah. No, I think it's roughly something like that. I mean, yeah. But I think we should look at. I mean, I still haven't. I must say that it's not completely clear. Like what exactly fixes this divergence. But yeah, we should discuss and figure this out.
Are there any more questions? If not, let's thank Abhishek.